Example 3 says find or evaluate the following using the theorem on the previous page. So in the last video, we learned about a three-part theorem that had some pretty important formulas on them. Let's use them to answer these questions. So in part A, we want to come up with a final value for the summation from 1 to n minus 1 of I squared. Now, this looks really familiar to part 2 of the theorem we saw on the previous page. So if you recall, the one on the previous page said that if we have the summation from I equals 1 to n of I squared, what that is equal to is n times n plus 1 times 2n plus 1 all over 6. So notice here that the only difference is that here our upper index is n, and here our upper index is n minus 1. So what we can do is we can use this formula, and instead of plugging in n, we're going to plug in n minus 1, since that's what our upper index is. Since notice that our lower index for both of these are the same, the only difference is the upper index. What that means is this is equal to, and again I'm going to use this formula right here. So I have n minus 1 times n minus 1 plus 1 times 2 times n minus 1 plus 1 all over 6. And I'm going to clean this up a little bit. That is equal to, notice that this second set of parentheses, I have minus 1 plus 1, so it's going to simplify to just n. And then I'm going to copy the n minus 1. And then if I distribute this 2 in, that's going to give me 2n minus 2 plus 1. And then if I simplify those, that would be 2n minus 1. And our denominator is the constant 6. That's not going to change, so I'm just going to leave that as is. So there is our final answer for part A. Now, another thing that we could have done is if our summation had an upper index of n, then what that means is we would have had this. And so we would have had n times n plus 1 times 2n plus 1 all over 6. But we really don't have the last term of that summation, since in reality our upper index is n minus 1. So another way you could arrive at this answer is by taking this formula and then subtracting off n squared. So it doesn't look like they're the same right now, but it turns out if you took this thing and subtracted off n squared, if you found a common denominator and simplified, this thing should simplify to the formula that we found there. So if you want something interesting to do or a challenge, you could show that those two things are equivalent. All right, so part B wants us to simplify the summation starting from I equals 1 to n of I times I plus 1 times I plus 2. And before we move any further, what we want to do is we want to multiply out this thing so that we get a polynomial in standard form. So what I'm going to do is I'm going to distribute I into that first set of parentheses. So if we do that, we get I squared plus I. And then I want to multiply out I squared plus I times the quantity I plus 2. Now, you can FOIL or however you want to multiply it. I like the box method. So on the left side, I'll put I squared and I. On the top, I'll put I and 2. Now, this is essentially just foiling, but it's a way that we can organize the terms that we're multiplying together. Now, in my top left corner of my box, I squared times I is I cubed. I times I is I squared. 2 times I squared gives me 2I squared. And then in my last box, we have 2I. And notice that these are like terms. So if I combine those, then we get I cubed plus 3I squared plus 2I. Okay, so this summation is equal to, make sure that you put either brackets or parentheses around the entire expression. Otherwise, it would be incorrect because the summation is being applied to the entire expression I cubed plus 3I squared plus 2I. Okay, what do we do from here? Well, now we want to use an even earlier theorem that we learned about in order to be able to write this into multiple summations. So using an earlier theorem, I can apply the summation to each of these terms. So I have the summation from I equals 1 to n of I cubed plus the summation from I equals 1 to n of 3I squared plus the summation from I equals 1 to n of 2I. Using that same theorem, but a different part of that theorem, I can factor out constants that are not dependent on my index. So now this is equal to the summation from I equals 1 to n of I cubed plus 3 times the summation from I equals 1 to n of I squared plus, I'm going to factor out my 2. All right, what do we do from here? Well, if you look at these summations, so this first summation, this second summation, and this third summation, we can rewrite each of those things using that same theorem we saw on the previous page. So let's go ahead and rewrite each of these things. If I sum I cubed from 1 to n, if you go back to the previous page, that is equivalent to n times n plus 1 over 2, and this entire quantity squared, plus 3 is just the constant, and then the summation, we actually used it in part A, so that was equal to n times n plus 1 times 2n plus 1 all over 6, and then we have plus 2 times, the last summation is equivalent to n times n plus 1, and this is all over 2. Now, we can clean this up a little bit since we have some multiplication happening. All right, so I went ahead and I made some space, and I can square the first term. If I do that, that's going to give me n squared plus n plus 1 squared over, our new denominator would be 4, and then 3 divided by 6 would leave a 2 in the denominator there, and then this 2 and this 2 will divide out. So we have plus n times n plus 1 times 2n plus 1 over 2, and then plus n times n plus 1. Now, I'm going to do something that is very incorrect, but I see it all the time, so please don't make this error. There's a 2 here and there's a 2 here. Those cannot be canceled out. So please don't make that mistake because of our plus 1 here. That would also need to be divided by 2. So please don't make that error. And I'm just going to go ahead and leave our final answer like that. All right, part C of this example we are seeing a limit for the first time included with our summation. So essentially we want to simplify our summation first, and then at the end we want to evaluate the limit. And it turns out that this is going to become a very important idea when we reach further topics in Calculus 2. So we have this, and this is equal to the limit as n approaches infinity of, I'm going to go ahead and square the thing inside the parentheses. So if we square I over n, that gives us I squared over n squared. And then we want to multiply that by 1 over n. So we have 1 over n times I squared over n squared. And if we multiply those, then in order to make that into a single fraction, that would give us I squared over n cubed. And notice that our index here is I, and n just represents a constant. And so based off one of the theorems that we saw earlier, I can factor out 1 over n cubed outside of my summation. However, you want to be very careful, because notice that in terms of our limit, we're looking at the limit as n approaches infinity. And so 1 over n cubed is a constant in the eyes of the summation, but it's not a constant in terms of the limit. So we can't factor 1 over n cubed outside of the limit. We can only factor it outside of our summation. But what's nice is if we factor out 1 over n cubed outside of our summation, we're left with the sum from I equals 1 to n of I squared. And we have a formula for that using that theorem that we saw earlier. So if I rewrite the summation of I squared, we know that that's equal to n times n plus 1 times 2n plus 1 all over 6. So let's do some simplification here. I have an n here, and I have n cubed in my denominator, so if I divide those, that's going to leave me with n squared. So I have the limit as n approaches infinity of, my numerator is going to have n plus 1 times 2n plus 1, and then my denominator is going to be 6n squared. Now, you want to recall back from Calculus 1, how do we evaluate this limit? Well, the thing inside the brackets is a rational function, and so if you wanted, you could multiply or FOIL out the numerator. If we did that, we'd get this is equal to the limit as n approaches infinity of 2n times n is 2n squared, and then plus 3n, and then our constant term would be plus 1, and this would be 6n squared. So we can see that for this rational function, the degree of the numerator and the denominator are the same. And if you remember from Calc 1, if the degree of the numerator and the denominator are the same, then the limit as the input approaches infinity is equal to the ratio of the leading coefficients, which is 2 over 6, and that is equal to 1/3. But could we have done that without multiplying out the numerator? So coming back here, I know that because I have an n here and a 2n here, that the degree of my numerator is going to be 2. So the first term is going to be 2n squared, and I know that I have 6n squared in the denominator. So essentially, I'm going to have 2n squared over 6n squared, and the n squareds, basically, because they're the highest powers in each the numerator and denominator, would give me 2 over 6. which is equal to 1/3. So that's kind of a shortcut on how we could have arrived there. But without the shortcut, this is the longer way, and we get that our final answer for part C is equal to 1/3.